Okay, now when you receive your little envelope through the post and open it up, there'll be nothing inside except one of those and a little plastic bag. Well, inside your little plastic bag you'll find 4 items. You'll find a piece of PVC tube, you'll find a small aluminium plug, you'll find a grub screw which is M3 by about 10mm long, and you'll find a 1.5mm Allen key. Now the first thing you must do is to first of all make sure you've got some bath sealant or something around you. This is Superflex Clear, it's a Loctite, but basically it's a bath sealant, a silicone bath sealant. You can use this, or you could use the stuff that came with your machine, the white sealant that's used to your high voltage sealant. Any of those will do the job. I advise you that the very first thing you pick up is this piece of black flexible tube, and you pop it over your K-type thermocouple. Make sure that the bulb on the end of the thermocouple is exposed, and we're going to slide that down this central tube here, and we should find that it goes in fairly smoothly, and you will find it hitting the end. You can feel it hitting the end in the middle here. Now we're now going to pop our little block of aluminium into the hole, a little plug of aluminium into the hole, and on top of that we're going to put the grub screw. Leave about 1/4 inch out, and then what we're going to do is put a small coating of silicone. Just around the thread. So I'm going to use the key just to drag that round and smooth it round there. Just clean my key with a piece of tissue, and then we'll screw the grub screw in. Now you'll feel it bottom out, and when it starts to go stiff, hopefully you're clamping the bulb right at the end there. Now give this a gentle tug here, and sure enough it's locked it in. Give it a little twist, and there we go. Your thermocouple is now installed right into the centre there. You've got good metal to metal contact, which means you'll get good quick thermal transfer. Now to finish off, what I would do is just put a little teeny weeny plug of silicone sealant in the top here, just to cover it over. Make sure you haven't got an air gap in there, and then just wipe away the excess. Okay, so that's now sealed the grub screw in, so that there's no chance of water ingress down there. This is a press fit in here, so you won't get any water ingress down here. And now you can see why we've put this on first, because now you're going to slide that forward and push it onto the end of your tube, and that will just give you a nice strain relief for this glass fibre covered cable. And there we go, there's your temperature probe assembled. Now we're going to take a look just for a moment at the various options that we've got on our little digital thermometer. Now if you look carefully, you'll see that I've strapped the second of my thermocouples onto the side of this digital thermometer, and what you can do is you can plug it into this T1 minus T2 connection here. This one here always goes in this left hand one, but make sure you get the connections, because there's a minus and a plus on the front here, which you need to put in the right way round. Now I've made a further modification to my unit, in that what I've done, I've actually painted my max min button, which is this middle button, with a marker pen, because it's very easy to press the wrong button here. There are only 2 buttons that you need to know about. One of them is the power button, which turns it on, And at the moment it tells me up here that I'm looking at T1. Now this is T1 and this one here is T2, and I can take a look at what T2 says. T2 says 12.9 or 13. So that's the air temperature. We'll turn that back to T1, and once we turn it on we can in fact press the max button like that. Now if I hold this for a minute, we shall see the temperature going up, and then I'll let it go and it will stop going up. And what it's doing, it's registering the maximum temperature that it saw. Now the great advantage here is we're also measuring the ambient via this one. So if we ask with this button what the difference in temperature between the ambient and that 18.2 was, if you remember this was 13. So technically we should see an answer on there of about 5 or 5.2. And there we go, 5.7. So something changed with the ambient after we looked at it. And that's the problem. It's a great idea because it means you don't have to remember anything. All you need to do is use that button to do your subtraction for you. But the problem is you can't guarantee that this here is measuring exactly ambient, because look, you could put your hand near it, it could be picking up anything. So I would suggest that you actually don't. I have experimented with this, and because you've got two sensors, you've got two possible errors, and then you've got this additional error that can occur because of ambient changes before you take your test. And although in principle it's a super idea, it's going to possibly give you inaccuracies in your results. So what I'm going to do is make sure that we only use one thermocouple. We're now going to load the doHICky test program, which is basically a timing program, and it's a program called doHICky. Right, now that we've got our program loaded, we shall need to edit it. We're only ever going to use one program. It will be suitable for all sorts of different applications. Sorry, we've got 0 to 40 watts, 0 to 80 watts and 0 to 160 watts. We've got 3 scales that we can choose from. What we're going to do initially is to suit this particular machine, which is a 60 watt machine, we're going to use the 0 to 80 watt range, which is basically the times 2. So we're going to edit the red layer, and to do that we push the button and we come down to the speed. Now at the moment the speed is 7 millimeters a second, which is the 0 to 40 range, and what we're going to do is move it up to 14. So 14 millimeters a second. And if you were calibrating your machine, you would start off at somewhere like 10% and you'd run a 10% test. Then you do a 10, you then do a 20, 30, 40, 50, 60 to, I mean, you can run up to 80 and 90%, but of course at that point you'll be overdriving your tube. Not a problem overdriving your tube for a few tests like this. So at the moment I'm just going to put this onto 65%. 65% will probably be somewhere in the region of maybe 70 watts. I don't know, without looking at my calibration graph, I don't know, but we'll check that out later because I don't really want to be influenced by anything at the moment. We're happy with 65, 65 and 14. So the test is now ready to run. Now before you run any of these tests, I would suggest that you drop your table right down to the bottom, as I have done, and the very least that you should do is put a piece of wood in the bottom. I'm not really going to recommend wood, but I want to show you what happens if you've got a fairly powerful machine, and I've got this running at about probably 60 watts, and I've got a 1.5 inch lens in here, which means that as it comes out it's starting to spread quite a lot very quickly. So there's a fairly diffused beam on there. I just want you to see what happens if you absorb that power onto a piece of wood with this program. So the program is only going to work over roughly a 1-inch diameter. So we're running this at 14 millimeters a second, 65% power. So the first thing that's going to happen is it's going to take about 10 or 12 seconds before it starts the program. And now it's starting the program. Can you see it scorching the wood now? In fact, it's just beginning to make the wood glow. There's a huge amount of power even at something like 10 or 12 inches away from that nozzle. What I would suggest you do instead of that is to get yourself a bowl of water. You need a pint or so of water at least, and this time we'll run the test. And here we go. Now I can feel no heat being reflected up here. Basically what I suggest you do is something like that before you start any of these tests. Then any energy that you are sending out will be absorbed into that water. You don't get reflections off the water, well, very little anyway. Okay, now what I have got here is something like about a gallon of water, which has been sitting in this workshop for a week or more. So basically I just leave it in here, and it assumes a reasonably good ambient temperature. So with our meter turned off, I should just stir that for about 15 seconds. That has now assumed an ambient temperature. Let's just check. We'll turn the meter on now, and that's about 11 degrees C. So what we've got to do now is to remember this number. It's settled down to roughly 11.2, and I will start the test off. Now, I don't have to panic because I've got, so what I'll do now is to press the max button, and it says 46.5. Take away 11 and we get 35.5, 0.2, 35.3, 35.3, double it, and that's 71 watts. Let's just see what 65% is on my chart here. 65% is 70 point, it's actually 71 watts, would you believe? Yep, 71 watts. So basically doubling the answer gives me the wattage. So I haven't even got a calibration chart with me at the moment. What I've got is in my mind 3 scales: 1 to 1, 2 to 1 and 4 to 1. If I run at 7 millimeters a second, I get a direct output. So let's set it and I don't know exactly where we're going to set it, but let's set it somewhere like about 15% and see what that comes out at on a different scale. So we modify the red layer. And at the moment it's sitting at 14 millimeters a second. So if we want to see the results coming out as 1 to 1, we need to change that down to 12.7 millimeters a second, which means it's going to take about, I think it's probably nearly 40 seconds to run the test. It's quite a long time. 15%. So before we start the next test, we'll turn the power off because that's the only thing that resets the max min. And we'll just pop this in here for 10 or 15 seconds. And we should find the result coming back to about 11. Just wipe it dry. Okay, we'll now turn on the power. And it says 12. Now, I'm not going to press the max button until we're ready to start the test. .3 max. So the last number I remembered was 12.3. .3, 17 point, 12.3, 7.7, 27.7, plus 0.9, 28.6. So that's 28.6 degrees. How close to 28.6 watts is it? We set this to 15%. And 15% is 26.2 or 3. But we're now going to change the settings so that the answer is 4 to 1. In other words, we're going to have to multiply the temperature difference times 4 to get the wattage. So we modify the red layer, and we need to change the speed to 28 millimeters a second. There we go, 28 millimeters a second, 80% power. That's about as maximum that's the maximum I can wring out of this machine. So we'll go through our same procedure again. We will, with the meter turned off, we'll just immerse this for about 15 seconds. 12.9, it's stable. It's about the right temperature. We'll start the test off. This is going to be a very quick test because there's so much power. We don't have to panic to start with. We press the max button. 12.7 to 32.7. That's very conveniently, so we multiply that by 4 and we get 80. Question is, how close to 80 watts does this machine deliver? Let's have a look. I set it on 80% and technically it's 76. So I'm about 4 watts adrift there, but of course with a multiplication factor of 4 you've only got to be a quarter of a degree out and you've lost a watt. So it's getting quite sensitive when you're working at high powers. Right, we've got this meter down to roughly ambient temperature by keeping it in there for about 30 or 40 seconds, because this one takes a lot longer to get the temperature down. fact it says it's about 78.4, so it's not far out. It's only 1.6 watts different. I've never claimed that this will be an absolutely accurate piece of measuring equipment, but it will put you into the right ballpark and it will get you within a few watts of the correct answer, as you can see from these little demonstrations. I have done quite extensive test work in the background. This was just a quick sample to give you peace of mind that multiplying by 1, 2 or 4 works. I shall provide a calibration graph as well, but you often don't need it. That's what I'm trying to demonstrate to you. So with this piece of equipment you should now be able to produce a calibration graph like this for your machine, which is the relationship between the programmed percentage across the bottom, the power in milliamps that it takes to drive the power in watts up on the blue line. And finally, if you can remember, we've got the water around the front, but that's really only a safety net, because most of the time there will be no power going around the front because it's being absorbed by the power meter, but it's just in case. Well, I hope you have success with your new toy. I only use this for absolute calibration. 99% of the time I'm using this on my ×2 range. I've supplied you with both an RD file, which will allow you to plug this program straight into your machine, or I've supplied you with a DXF file just in case you don't happen to be using RD Works. But what I need to do is to show you how to run this program, or how to set this program up. Here we've got the 3 main scaling factors that I'm going to be using this program for. If you're going to use it on a one-to-one basis, i.e. whatever you read the temperature difference as is the wattage, or when you look at the temperature difference you multiply it by 2 and that's the wattage. If you've got a high powered machine, something over maybe 120 watts, then you would use the 28 millimeters a second feed rate, which means you take your temperature difference and you multiply it by 4 to get the wattage. Now the whole point here with this doHICky and why we've got these different ranges is because you don't want to heat the block up to more than about 60 degrees C. Provided we can stay in the 40-50 degrees C temperature region for the end temperature on the block, then we stand a good chance of keeping everything fairly linear. So that's why I've used these 3 ranges. So the first one, for instance, may be up to 40 watts. The second one probably is up to 80 watts. And the third one is up to 160 watts. We don't need this information now, so we can throw that away. But what we do need to do is to take this middle line here, which is our slow approach. This is our breathing time after we press the button. We get time to relax and get the doHICky into place to take the measurements. So we'll set that onto a blue layer, and then for convenience we'll set the actual pattern onto a red layer. Let's look at the blue layer first. We are going to use it as a cutting layer. We're only going to set the power to about 1%. Now at 1%, nobody's machine is actually going to fire the laser, but the machine doesn't know that. So we're going to have is output yes, processing mode is cut, and 1%. Now here's where you can make a decision for yourself. That blue line is about 12 millimeters long, so that means you've got 6 seconds of preparation time to get your mind into gear, or you can have it set to 1 millimeter per second, which means you've got 12 seconds to relax and get yourself into place before the test starts. That's the favourite, but it's up to you. And now we look at the red layer. Obviously it's going to cut, is output yes, it's going to be cutting. So when it comes to running power tests, you will be in control. Therefore what you will do, you'll set this minimum and maximum power to a series of values so that you can probably calibrate your machine. In other words, you would set this initially to maybe 10 and then 20, 30, 40, 50, all the way up to 100% by editing it on the machine and running the test. So that speed could be set to 7, 14 or 28, depending on which range of power you want to be working in. I'm going to set it to the middle range, 14, which is where I do most of my work. And I'll just remind you again, this takes me up to 80 watts without overheating the block. Now we need to make sure that we do the blue cut before we do the red cut. And to order my cuts now, just by habit, I always use the grouping technique, which basically means that I will select that blue line and I will put it as a group, and I will select the red line and put it as a group. And now I'll go to this piece here, which is edit cut properties, and we get this list. And what I can do, I can choose this item first and put it into a new list, and then I'll choose the spiral and put that into the list. Job done. Okay, so now I know without any doubt that the order in which these things are going to run. Right, before we save this program, we must do one thing, and that's our green dot. Now at the moment our green dot is showing on the top left. It's going to be much more convenient for us to cite that green dot in the center of the pattern. And to do that, what we should do, this is where the program will be written from, by the way. The machine will decide that it wants to start from the center of the pattern. And to do that, we shall go into System Settings, and we will just choose this lacer head to the center point. And there we go. So now the green dot has moved to the center. Now we can save our file to a U file. Now you've seen me up to now demonstrating power coming directly out of the laser tube itself. You can use this after mirror 1, after mirror 2, and you can remove the lens or the nozzle and use it after mirror 3. When it comes to using it after the lens, what I would advise is caution. If you put too much power on the anodized surface, you will actually etch the anodizing off. So if you, for example, got a 2-inch focal length lens, which has got normally a focal point about 3/4 of an inch in front of the nozzle or below the nozzle, then make sure that you hold this doHICky about 4 inches or so below the nozzle and move it around. If you see any marks appearing on the surface, you're too close and you will be damaging the surface. So just be ultra cautious when it comes to checking power after the lens. And apart from that word of warning, go forth and enjoy. I'm glad that I've been able to share this experience with you, and thank you very much for joining me.